In this video, we're going to talk about implicit differentiation. So before we dive in, I just want to say you're halfway through calculus if you're watching this video, and that's really awesome. So I think we have 21 lessons in this whole course, but you're on lesson 13, so keep up the work. By the end of this lesson, you should be able to answer the following little question. What is implicit differentiation and why is this strategy necessary for finding derivatives? And by the end of Unit 3, we're continuing answering the following big questions. How do we make finding derivatives easier? And what is the point of finding derivatives? So let's start with the warm-up and review the differentiation strategies that we learned in Unit 2. So first of all, we had sums and differences, which we did term by term. We had the constant multiple rule, which meant constants go along for the ride. We had the power rule, product rule, quotient rule, and chain rule. But it turns out these are not the only strategies that exist for taking derivatives. In this unit, so those 6 were like our basic rules. In this unit, we're going to learn about 2 other strategies which sort of involve combinations of these still. The first, which we'll learn about in this lesson, deals with implicitly defined functions. Okay, so even though this is its own differentiation strategy, it could involve product rules, it could involve quotient rules, it could involve power rules, and it could involve chain rules. And as always, it definitely could have multiple terms or constants in front of any of those functions. So we're still using the 6 rules from before, but we're doing it with a different type of function. So an implicitly defined function is a function in which some variables are functions of x, or the independent variable. So maybe your independent variable is t. That's another common one. So t is also common. And your dependent variable doesn't have to be y. So we're going to see later that we have word problems in which we could give different names to our variables besides x and y. And I think as you work through the pre-recitation prep, you're going to find that you might have things like area, which you probably want to call a, or you might have volume, which you want to call v. Okay, so it's not that we always have x and y, so it's important to know what is your implicitly defined variable and what is the implicitly defined variable a function of. Okay, so for example, so what is an implicitly defined function? Well, if we look at the function x cubed plus y cubed equals 6xy, this is an implicitly defined function. So notice we don't have y equals some function of x. The x's and y's are all mixed together on both sides of the equal sign. However, if we look at y is equal to 6x plus x squared, this is not implicitly defined because we have y on one side, x is on the other side, so y is a function in terms of x, and it's very clear. So let's try an example. Let's solve the equation x squared plus y squared equals 25 for y explicitly in terms of x and find y prime. So y in terms of x means that we want something that looks like y equals and then a bunch of x's. Okay, so dot dot dot. Alright, so if we start with x squared plus y squared is equal to 25, and we want to solve for y, we could move the x over, so we'd have 25 minus x, and y is equal to plus or minus the square root of 25 minus x squared. Okay, so we've solved for y. That's y explicitly in terms of x. Now we want to take the derivative. So y prime is going to be Well, first let's change y into a power. So we have y is equal to plus or minus 25 minus x squared to the 1/2. So y prime is going to be plus 1/2 times 25 minus x squared to the minus 1/2 times negative 2x, and that plus or minus is still out front. So if we wanted to start thinking about simplifying this, so I'm going to go back up to the top here. When we multiply this negative sign times the plus or minus, it sort of switches it around to a minus plus. And we've kind of seen that before with our true facts on limits. Also, the 2 and the 2 will cancel out, and so we should have minus or plus x over the square root of 25 minus x squared. Okay, so that's our y prime. Now, that one wasn't so bad. So we were able to solve for y, we were able to take the derivative, and you're probably like, well, that's exactly how we've been doing things. And you would be right. But it turns out that not all implicitly defined functions are explicitly solvable. So that method is what we did in the first example. Great, you can use it for explicitly solvable equations. But like I said, some implicitly defined equations are either unsolvable or extremely complicated. So even that one wasn't super nice. So if we had worked that with implicit differentiation, it would have been a bit shorter and nicer. But as an example, if we have something involving a fifth power like this is not solvable for y. We don't have any way to do it. And actually, mathematicians have proved that that is actually impossible. So for equations like this, we need the different differentiation strategy called implicit differentiation. And what this allows us to do is actually differentiate from the form where all of the x's and y's are mixed together, which is super nice. So no solving necessary until after you take the derivative. So rather than go into a bunch of theory, let's just dive into some examples and see how implicit differentiation works. Okay, so for our first example, we want to find y prime if x squared plus x is equal to y squared plus xy. So the first step of implicit differentiation is take the derivative of everything in the equation, but we're going to treat y like a function of x. So when we take the derivative of something involving y, we have to remember that y is a function of x, so its derivative is y prime always. Okay? So let's start with the first term. So x squared is going to give us 2x. Plus x, the derivative of x is 1. The derivative of y squared is 2y. But what I really have here is f of x quantity squared. So I really have this chain rule hidden in here. So once I've done 2y, I have to multiply by the derivative of y, which is y prime. And then finally, when I see x times y, that's going to be a product rule. So I'm going to have x times the derivative of y, which is y prime, plus 1, which is the derivative of x, times y. So that is my derivative taken implicitly. Now, once we take the derivative implicitly, we actually need to solve for y prime, because otherwise we don't know exactly what the derivative is. So once you've solved for y prime, you'll have an explicit derivative of y equals function, right? So it's important that we solve for y prime next. Okay, so let's rewrite our derivative from the first step. And I want to solve for y prime. So the first thing I notice is I have two terms that have a y prime. But my goal is to get this down to one term with a y, or not one term, but one y prime in the whole equation. So I can't add those things together. The best I can do is try to factor out the y prime. But to do that, I'm going to need to get rid of everything else that doesn't have a y prime. So if I move over that positive y, I'll get 2x minus y plus 1 is equal to 2y y prime plus xy prime. And now I can factor out the y prime. So I have 2x minus y plus 1 is equal to y prime times 2y plus x. And my final step, I can divide by that entire factor on the right side that is not y prime. So my final answer is 2x minus y plus 1 over 2y plus x is equal to y prime. So this is my derivative. Okay, let's try another example. So this one will be a little bit tougher. So this time we have find dy dx if sine of x plus y is equal to y squared times cosine x. So once again, we want to take the derivative, remembering y is equal to f of x. And here we're seeing this Leibniz notation again. So just remember, this is a nice notation, even though it looks kind of clunky, it's actually really nice. And that's because it kind of reminds us that the derivative is a slope. It reminds us that we have a change in y over a change in x. So first, again, we want to take the derivative. So this sine term here is going to involve a chain rule. So first we want to take the derivative of sine, leaving the inside the same. So that's going to be cosine of x plus y. Then we want to take the derivative of x plus y. So it's going to be 1 plus y prime. And now I want to work on the right side. So y squared times cosine x is going to be a product rule. So first I leave y squared the same, take the derivative of cosine, which is negative sine of x. And then I want to take the derivative of y squared, which is 2y, y prime. And then finally I want to leave cosine x the same. So that is my entire implicitly taken derivative. However, now I want to, oh my bad, I'm really sorry here. I wanted to do Leibniz notation in this. So instead of the y primes, we're going to write dy dx, just so we get used to that notation. Okay, so now I want to solve for dy dx, just like I solved for y prime in the previous example. So let's rewrite our function. 1 plus dy dx is equal to y squared. Actually, let's move the negative sign to the front. So we have negative y squared sine x plus 2y dy dx cos x. All right, so first of all, I noticed that I don't quite have the situation of the previous problem. So I have like two things with a dy dx. So I have this thing and I have this thing, but the one on the left is not completely multiplied out. So I can't just start moving things around without distributing the cosine x plus y through that sum. So that's going to give us cosine x plus y plus cosine x plus y dy dx is equal to negative y squared sine of x plus 2y dy dx cosine x. And now I can start to do what I did in the previous problem, which is get everything with a dy dx on the same side of the equation and everything without a dy dx on the opposite side of the equation. So I'll have cosine of x plus y times dy dx minus 2y dy dx cosine x is equal to negative cosine x plus y minus y squared sine of x. And finally, I can factor out the dy dx. So I'll get cosine x plus y minus 2y cosine x is equal to negative cosine x plus y minus y squared sine x. And I can divide by that factor that's left over. So I have dy dx is equal to negative cosine x plus y minus y squared sine of x all over cosine x plus y minus 2y cosine x. And this is my implicitly solved for derivative. Okay, let's try another example. So this time we're going to see what happens if we try to tackle a higher order derivative. So I know we haven't done too much of this in class, but it's definitely been in your homework. And remember that when we have a higher order derivative, it just means we're taking a derivative of a derivative. Okay. So we're going to start this problem off just like the other two. We're going to take the derivative, remembering y is equal to f of x. And you might start to like this one because this function is going to be a little bit easier than the ones we just did. So we take the derivative, we have 4x cubed plus 4y cubed y prime is equal to 0. And we want to solve for y prime. So I can move over that right term. So I have 4x cubed is equal to negative 4y cubed y prime, and I can divide by negative 4y cubed. So I have 4x cubed over negative 4y cubed is equal to y prime. And last step is I can cancel those 4's. So I have negative x cubed over y cubed is equal to y prime. Okay, so this is y prime. So that's my first derivative, and I don't want to box that because that's not actually my answer. Now I want to find y double prime. So there are two routes you could take for this problem. You could start with, so maybe I'll do this in different colors so we know that it's not part of the problem, it's just me talking. So here we could take y double prime here, but if the function was more complicated, this would be a bad idea. Okay, so we could start with the explicitly solved derivative, and we could take y double prime, and you're probably like, oh, that wouldn't be too bad. That would just be a quotient rule. But what I want to do is instead take the derivative here, because if you had a more complicated function, that derivative that solved explicitly would be an absolute nightmare. So I want to show you how we take the second derivative implicitly as well, and then go back and substitute in y prime so that when you get to more complicated problems on your homework, you'll have something to look at. Okay, so we're going to find y double prime in terms of x, y, and y prime, but we're going to do it implicitly. So we're going to start with that first step with the y prime instead of the explicitly solved step. Okay, so now that we have that out of the way, let's actually go ahead and take the derivative. So the derivative of 4x cubed is 12x squared. And then the derivative on the right is going to be a product rule between y cubed and y prime. So we copy negative 4y cubed, and we take the derivative of y prime, which is y double prime. And then we take the derivative of negative 4y cubed, which is negative 12y squared, y prime. And then we keep y prime the same. Okay, so this is like here times y prime. All right. But I'm going to erase those parentheses so that my work isn't too confusing. But just know that that's how we grouped it together to do the product rule. Okay, so now I found y double prime. So now I want to actually solve for y double prime, because remember, I haven't actually found my derivative until I've explicitly solved for it. So I can move over the term with the y double prime. So I have 4y cubed y double prime is equal to negative 12x squared minus 12y squared times y prime squared. Yeah. And I can divide by 4y cubed. So we have y double prime is equal to negative 12x squared minus 12y squared y prime squared over 4y cubed. And I can simplify this a little bit more by canceling the 12's with the 4, and so we get 3's on top. So we finally have negative 3x squared minus 3y squared times y prime squared all over y cubed. So that's my second derivative, but just like the first derivative, notice that we only had x's and y's in that formula for the first derivative. I want to do the same thing with the second derivative. So I want to substitute my expression for y prime into the y double prime answer that I got. So we have negative 3x squared minus 3y squared times negative x cubed over y cubed squared all over y cubed. So that's substituted y prime. So now I only have x's and y's, and now I just want to simplify. So in this unit, simplifying is going to be pretty important. I don't think you still have to simplify all the way on your WebAssign homework, but I would practice it just so that when we get to the later things in Unit 3, you'll have that practice under your belt. So to simplify, let's go ahead and square that x cubed over y cubed. So we have negative 3x squared minus 3y squared times x to the 6th over y to the 6th all over y cubed. If we multiply that fraction times the negative 3y squared, we get negative 3x squared minus 3x to the 6th over y to the 4th, all over y to the 3rd. So my final second derivative is negative 3x squared over y cubed minus 3x to the 6th over y to the 7th. All right, and so this is my final answer. Now, implicit differentiation can also help us solve problems involving real-world scenarios. So sadly, in this example, I think our variables are still going to be x and y, but as you work through the pre-recitation prep, this is where you're going to start seeing functions that don't always have x and y as your variables, because we're going to be dealing with areas, volumes, surface areas, Pythagorean theorem, so you're going to have all different kinds of variables. So let's dive right in. So a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? So when we're dealing with a word problem, the first thing we always want to do is draw a picture. So I have my wall, I have the ground, and I have my ladder leaning against the wall. Okay, so this ladder is 10 feet from the word problem, so that length must be 10 feet. Now, I want to label my rates in a different color so that we're not confused. So the tricky thing about these pictures is they're always not going to move, but in the problem we're always talking about movement. So what I like to do is use a different color for my rates versus my static picture. Okay, so the bottom of the ladder slides away from the wall, so I'm going to indicate the direction, and I'm going to write the rate. So if it's sliding away from the wall at a rate of 1 feet per second, I'm going to call that distance x. So actually, let me go back to blue for a second. I'm going to call this distance x and this distance y. And so the rate of x with respect to time is going to be dx dt is equal to 1 foot per second. And we want to know how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall. So dy dt, so the rate at which the ladder is sliding down the wall, we don't know. So we're just going to label that with a question mark. And finally, we want to know at the exact instant where x is equal to 6 feet. Okay, so that's my picture. So I have my rates, I have my static conditions. So let's now think about an equation that we could use to relate the blue quantities. Okay, so that's also why I like to do the rates in a different color, because we're always going to start by thinking about how can you relate the things in the static picture. So if we want to think about how to relate the distance y, x, and 10 feet, we might notice that this is a right triangle. And so my first instinct would be you have two sides of a right triangle. You could find the third side, but we don't really care about that. We just want the equation. So I want to relate all three sides of a right triangle. The first thing that comes to mind is Pythagorean theorem. So I can write x squared plus y squared is equal to 10 squared. Now, somehow we want to get rates involved in this equation that we've used to relate our picture. So we're going to take the derivative, and that's going to make our rates pop out. So if we take the derivative of the equation, notice this is going to have to be implicit because x and y are both on the same side. We got multiple variables going on in this function. We want to notice which variables are defined implicitly. So the trick here is if we look at our rates, so the dy dt and the dx dt, notice that both of those rates involve time. So x here is not your independent variable. It's actually another dependent variable along with y, meaning that both x and y, when we take the derivative, it's going to have to be done implicitly. So when I take the derivative of x, I'm going to get 2x dx dt. And when I take the derivative of y squared, I'm going to get 2y dy dt. And that's equal to 0 because the derivative of 10 squared, that's just a constant, so it's 0. Okay, so now I have my equation that's going to relate every single quantity in my picture, both the red quantities and the blue quantities. So I want to substitute everything I know and figure out what I still need to find. So let's see what we can do here. So we have 2 times 6 because we know we wanted x to be 6, times 1 because dx dt is 1, and our units there are going to be, let's see, let me go back and do that with units. So we have 2 times 6 feet times 1 foot per second plus 2 times y times dy dt is equal to 0. Okay, so what you might notice in this equation is we still don't know y, so we need to figure out what y is. And how can we do that? Well, remember we had that initial equation, Pythagorean theorem, where we related x, y, and 10. So what we can do is go back and use that equation and plug in what we know. So we have 6 squared plus y squared is equal to 10 squared. So we have 36 plus y squared is equal to 100. And then 100 minus 36 is 64. So y is equal to 8. 8 feet. So we want to be very careful with units in these word problems. So I can go back to my derivative, or I shouldn't say derivative, but equation involving rates now, and I can plug in my quantity for y. So this is going to give me 12 feet squared per second plus 2 times 8 feet times dy dt is equal to 0. Okay, now this gives me 12 feet squared per second plus 16 feet times dy dt is equal to 0. So I can move over the right side, and so I have, or actually let's move over the 12 feet squared per second. So we have 16 feet times dy dt is equal to negative 12 feet squared per second. I can divide by 16 feet, so I get dy dt is equal to negative 12 feet squared per second over 16 feet, and that's equal to negative 3/4 feet per second. So once we divide by that unit of feet, we get back down to feet per second, and that's exactly what we want, because if we're looking for a rate of distance with respect to time, we better not have any squared distance units. So that is the rate at which the ladder is sliding down the wall. And so let's just really quick make a comment about the negative in this answer. So negative makes sense because sliding down the wall. Okay, so that is an introduction to implicit differentiation. And that's the end of lesson 13. But make sure that you go and do the check your understanding to make sure that you understand what was discussed in this lecture.